It turns out that trigonometric functions like sine, cosine, and tangent have their tentacles in pretty much all of calculus and physics because, of course, calculus and physics run hand in hand. That means that there are deep connections that we can make between the trigonometric functions and all sorts of topics through all of the different calculus courses. That means that we have to learn one more set of derivative rules, though, the inverse trig ones. So recall just from your pre-calculus class that a trigonometric function like sine, cosine, tangent, they all are take an angle as their input. So these would be sine, cosine, tangent, right? Those operations. I'm just going to put etc. Secant, cosecant, cotangent. They take an angle and give you back a ratio. So sine, for example, gives opposite over the hypotenuse. Cosine gives back adjacent over the hypotenuse, etc., etc. Okay, so the inverse functions reverse that process. So they will take a ratio and give back the angle. So let me mention that. So the inverse trig function will take the ratio as the input and give back the angle as the output. Right? That's how trig functions work, and that's how inverse trig functions work. All right, now there's one other issue though, and that is that to make this work, in order for an inverse trig function to exist, it has to be an inverse function first and foremost. And inverse functions require that we restrict the domain. Oh, one other thing real quickly. Inverse notation is with the little put -1 power. And that's fine. We use those a lot. Me personally, it's not my favorite notation. I'll use it if I have to. But I'm more often using the arc notation, ARC. So putting that in front means inverse. They are one and the same. So either notation is fine. It's just a personal preference. All right, so we have to limit our domain and ranges in order to make this work. Let me show you what I mean in Desmos. Okay, so I'm going to just show you this graph here. I'm going to turn off the inverse trig function for just a second. And I'm looking at sine, but I could look at all sorts of functions. It doesn't really make any difference. Cosine, tangent, cosecant, they all have patterns. And that's kind of the problem, right? So sine has this kind of wave pattern. And the problem is, if you remember from your pre-calculus class, in order to have an inverse, you have to be 1 to 1. In other words, it has to pass the vertical line test, i.e. be a function in x, but it also has to pass a horizontal line test and be a function in y. That way, well, it would have an inverse function at all. And the way we accomplish that is basically by restricting ourselves and from one low point down here at negative pi over 2 negative 1 to a high point of pi over 2 1. If we just look at that section and nothing else, then we'll be fine. So that's what we do. So we say, okay, rather than looking at all of sine, I'm just going to look at that section of sine. Oops, I'm going to make that black so you can see it right here. So I'm just going to look at that piece of it. And if I look at that piece of it, then that'll be great. I'll have every possible sine value from -1 to 1, and it passes the vertical line test and the horizontal line test. And I'm leaving in the y equals x line just to remind you that the two functions, the sine and the arc sine function, should be mirror images of each other, should be symmetric across that line y equals x. And sure enough, they are. Right? Those two functions are mirror images across the line y equals x. They are indeed inverse functions. Inverse functions, if you remember, have the domain and range flipped. So, for example, this sine has a domain of negative pi over 2 to pi over 2. So over here on the left, that's negative pi over 2, negative 1.57. And then over here on the right, positive pi over 2. That means that if that's the domain of the original function, then that's the range of my arc function. So you can see the y value is negative pi over 2 to the y value is pi over 2. And the same is true in reverse for the range. So the range is from -1 to 1 in the original sine function. So then it's therefore the domain is -1 to 1 in the arc sine function. So the domains and ranges reverse in a function versus its inverse. And that is what is being mentioned all through this page. So the domain of the sine function is the range of the arc sine function, and so on, right? The domain of the arc sine is the range of the sine, and that's true for all 6 of these graphs. Okay, so then let's think about let's just consider arc sine. What I'm going to show you for arc sine works for any one of these 6 functions, but I'm just going to show it to you for arc sine. All right, so remember we have our restricted domain, right? And this is sine of x right here. So arc sine of x would kind of come through. And instead of going from negative pi over 2 to pi over 2, it's going to go from negative 1 to 1. Oh, sorry, from negative 1 for your x to 1 for your x. And then it'll end up over here at this point. And so they kind of mirror image each other, right? Like that. I'm not doing a very good job of drawing it, but you get the gist. So that would be the arc sine of x. Okay, so wonderful, lovely. But that means that the derivative of this thing is going to be a little weird. And honestly, I'm not going to derive it. To derive it requires some trickery. It basically requires us to use 2 different functions simultaneously, as well as trigonometry, a triangle. And so I'm just not going to do it. It requires something called trig substitution, trigonometric substitution, which if you could take calculus 2, you'll learn. So I'm not going to do it. Boo. So meh, let's not do it. Let's just say what it is. So, and the derivative of sine, here I'm going to put it right up here. The derivative with respect to x of arc sine of x is equal to 1 over the square root of 1 minus x squared. You could prove it using basically everything you know from trigonometry as well as implicit differentiation, but I'm not going to bother. Just let's just see it, right? And let's just test that it works, what I'm telling you. So my conjecture is that this is the derivative, this 1 over 1 minus x squared is the derivative of arc sine. And then let's just prove whether I'm correct by considering the slope. But it's kind of boring to look at it on a sheet of paper, so let's go look at it in Desmos. All right, so I've got my inverse function. I'm going to turn this off because I don't need to see that anymore. And I want to look at the tangent line at particular points. And I'm going to visualize the derivative function right here. So this derivative function that I'm graphing is 1 over 1 minus x squared. I want to kind of prove that this is going to work. So if you look here, let me change my scale real quick. So I need to see a lot more in the y direction. There we go. Okay, so the blue curve right here is my arc sine function. And then this is my tangent line at a point. So if I drag this point along, you can see the slope. You can see the blue curve is constantly increasing, right? So since the blue curve is constantly increasing, my derivative is always positive. The derivative is the green one up here. All right, then look at the slopes. So right here, at x equals negative 0.52, my y value is negative 0.547. But the slope of this is positive 1.17. And then as I go closer to 0, it's getting smaller and smaller and smaller. At 0, the slope is 1. And then as I move away, it's getting steeper and steeper and steeper again. And at the very end, it gets very, 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 very steep. It shoots up, right? 3, 3.5, 4, 5, and so on. And that's exactly what's happening. So you can see that this graph is in fact working, that the y value here, the 1.003, is in fact the slope of the tangent line to that arc function. So there you go. I'm proving it, quote unquote. Not really proving it, but I'm proving it as much as I want to prove it. So there you go. So, yes, it works. So the slope of this line, I've just got one static graph of what we were just looking at. So the slope of this line is in fact equal to that y value, f prime at a, right? That derivative right there. All right, and then that means that there's a ton more of them, and these are not ones that have to be memorized. They just are. I will tell you that they show up a shocking amount. You'd be amazed at how often these ones show up. That's because trigonometry, like I said, has lots of applications. So therefore, also do the arc trig functions, and therefore so do their derivatives. So let's just practice with one real quick. And I'm actually practicing with the arc sine, but I could have used any one of them. It doesn't make any difference. So if I look here at arc sine, the derivative of arc sine is 1 over the square root of 1 minus x squared. So when I have this and I want to find the derivative, that would be, well, it's a constant multiple, so 7 times, and then 1 over the square root of 1 minus. Instead of x, I have a function, 2x. So I'm going to put 2x squared. And then, of course, that's not just regular x. Oh, I'm so sorry. That's off screen. So 7 times 1 over the square root of 1 minus 2x squared. And then I need to use the chain rule because I'm multiplying by the derivative of the inner function. This is an inner function right here. So I need chain rule right here. And the derivative of 2x is 2. So that means 7 and 2 are both in the numerators because this is over 1 and this is over 1. So that's 14 over the square root of 1 minus 4x squared. And we're done. Easy as that. And in a way, if you look at the list of all the derivatives, which I have right here, and boy, have we come a long way since having to do the limit of the difference quotient for every one of these. We just learned the last 6 in this list: arc sine, arc cosine, arc tangent, and so on. And again, those 6 do not need to be memorized. You just have to use them. There is one other one that kind of shows up that we've kind of skipped over, and it's right here. Right there with the absolute value, and I have an example of that down here. You'll notice that these particular ones are listed with u, which actually makes more sense. Like, for example, in the one we just did, u was equal to 2x. So we did 2x quantity squared times u prime, which was 2. That's what we just worked on. All right, so I just want to give us one example of rule number 6. It's an oddball rule that doesn't really fit anywhere else, so it's the absolute value rule. Okay, so if I look at this particular one, I want to find f prime. So I want to find the derivative of that. So this right in here is my u, right? So I'm taking the absolute value of u. So according to rule number 6, what I would do is u over the absolute value of u. So it'll be 3x squared plus 5x over the absolute value of 3x squared plus 5x times u prime, which is the derivative of that inner portion, which would be 6x, because you bring the power down, 6x plus 5. And I'm putting that in parentheses because, well, let's see, this is u over the absolute value of u. This right here is u prime, and you have to multiply all of it by u prime, not just the part that makes you happy. Plus, trick question, 0, because e to the 4th is constant. So we actually don't need that at all. It's done. Right, that was a little trick to try to trap you. This is constant. Therefore, it doesn't have a derivative. Well, it does. The derivative is 0. And you're done right there. Just leave it, as ugly as that might be.